Thanks a lot. Yeah, thanks for the invitation, and it's been a great joy to be here for the last couple weeks. Yeah, so my talk's going to be about the derived Tate curve, which is some spectral enhancement of the ordinary Tate curve. So let me start there. So what is the Tate curve? Is an elliptic curve. Which is defined on the power series ZQ, and it's defined by this following equation: y squared is x cubed plus some coefficient a4.6. And these coefficients we can write in the following way. This part, it's not I need my notes. I've actually got these coefficients memorized.
What's the symbol in front of the first summation? So
it's a 5.
That's a 5.
Before into the picture, it's not a 7. That one? That's a 7. Probably isn't a 1. Okay. There's no actual point for me to write these formulas, just scare you a little bit.
Oh, wait. The denominator of the second one, is that an exponent?
No.
No.
Oh. All right. In fact, I lied to you before and after. It's not quite an elliptic curve. It's called the generalized elliptic curve because it has a nodal singularity at q equals 0. But we essentially just exclude that point, and we do get it is. Let's take T. I'm going to put a little heart over it. For people who know this game, they know that later I'm going to define a T without a heart. Okay, so this elliptic curve is very important in the theory of elliptic curves. For example, if we pass to right, it's classified by amount from spec C Q to moduli set elliptic curves. And if we pass the global sections, we get a curve that takes a modular form to its cubes. And this map is used to study elliptic curves. Okay. Another thing you can use this for is you can use the compact this moduli elliptic curves. For example, essentially, this generalized elliptic curve over this ring is a universal elliptic curve with a nodal singularity. The moduli stuff. Generalized elliptic curves. That's the push out. And this is some nice application of moduli. So all of these structures have analogs in the world of spectrum.
What is this a push out of? As
It's a push out of stacks. So you just take a push out in, in your functor of points, and you can prove this is again delete ones. And so this bottom map, it induces a map, which is another Q expansion map. Now this is a meromorphic Q expansion map. My modular forms are allowed to have pools at 0, and here they no longer have pools. All right. Let me discuss the extensions of these to elliptic cohomology theories. So I'm going to define two spectra. Okay. And in each case, I can just define them by base changing KO Q applied to some finance W complex, which is KO X, and my base change over Z. This map is flat, so this again defines cohomology theory. And so these are cohomology theories. They define spectra. Okay. We have the following constituents. There exist topological Q expansion maps. So these rings of modular forms, they admit enhancements to spectra, these so-called topological modular forms, and also these Q expansion maps. In both cases, here this is essentially, should be the global sections of some spectral version of this stack, and here similarly, we expect this to be global sections of some spectral version of this stack. Okay, but these maps are originally constructed by some sort of obstruction theory. And essentially, what I want to tell you now is about a way to construct these maps which doesn't use any obstruction theory, and instead uses the world of spectral algebraic geometry. Right. So at least this object here, capital T1, it has been constructed in a different way. It originally was constructed by obstruction theory, but now Lurie's given us a different way to think about it. For this is what it was. Let's just say that. Yeah. So what does he prove? Exists. The numbered stack. And now 4. Represents so-called oriented elliptic curves. So this is a generalization of the notion of an elliptic curve to the world of spectral algebra, where instead of basing our geometry on ordinary rings, we base them on E-infinity rings. We take the global sections of this stack. We represent this object topological modular forms. So this is, I think, much more than just another construction. In fact, it opens up many different avenues for exploration. And one that I want to highlight here, which is, I guess, especially important to us as equivariant homotopy theorists, is this one here, equivariant elliptic homology theories. What do I mean by that? The existence of an actual universal elliptic curve over this stack is what we use to produce our equivariant elliptic homology theories. I want to just quickly state that in the following theorem, which was originally sketched by Lurie, proved by David Gecker, and then with some more. There's an extra epsilon for the statement that I'm writing here. It was proved by David, me, you. Not. So what's the statement? There's an assignment of oriented elliptic curves to global spectrum. In fact, the infinity allocates global spectrum. So it takes something of the curve over some stack S, and it spits out something we could think of like the global sections, but now enhanced to a global cohomology theory. These provide integral enhancements of equivariant elliptic homology theories.
What does it factor through? And there's a functor, but presumably.
Yeah, so I have to a little bit. It's, let's say it's a functor of here I put elliptic curves and base change of curves. So like you could say it's a functor from the unstraightening of, you take stacks and you take the functor which sends it to the groupoid of elliptic curves. And in base change you can unstraighten that, and then you're writing this down as a functor of that. So I think the precise functoriality of this assignment in more interesting maps of elliptic curves is unclear. It's something to think about. I mean, something I've been thinking about. Let me just.
You want to relate this not to the previous stuff. I can just.
Yeah. So of course, there's many properties of this assignment that one might expect. So, for example, I can tell you if you take this and you take its A fixed points, then this is homomorphisms of driving dual A as a constant group scheme into your elliptic curve. And this is for a compact group.
Set into global spectrum. So you take the global section of the structure sheet of part A.
I should take a close. Of course, an example, the universal example, is you get some slightly beefed up version of TMF living inside of this category of clues. So there's much to be gained for linking constructions from the world of classical elliptic curves to this spectral version. For example, we get equivariant refinements of everything that we're interested in. And so that's what we're trying to do. We're trying to essentially lift these maps to the world of spectral algebraic geometry and as a consequence, obtain equivariant refinements. So let me state that here. So there exists an oriented elliptic curve T living over. Nobody, here I actually have to take this step.
Could you remind us what oriented means?
Hmm?
Could you remind us what oriented means?
Right, so oriented, roughly, if I have an elliptic curve. So the idea of an orientation is I have some elliptic curve which is living over, let's say it's living over a spectrum. So this R is going to be infinity ring. And what I can do is I can extract from this formal completion as 0. This gives me some formal group. And what I want this elliptic curve to be is essentially an enhancement of the formal groups that we normally see in topology. So essentially what I ask is I ask that this thing is complex oriented. And then if it's complex oriented, it always has this equivalent. There's some object which you might this. This is the equivalent formal group law associated to this E infinity ring. And you ask that the completion of E at the point is equivalent to this. In fact, orientation is the choice of such.
Let's try to unpack what that formula says with the contracting tool.
This here. So an important case is if you take S1, then the Pontryagin dual is just Z, and maps out of Z is just free on a point, so it's just your elliptic curve. So the S1 fixed points of this global spectrum we get is just the global sections of your elliptic curve. And if you now plug in, let's say, some finite group, then you're getting global sections of its like n torsion, plug in Cn. And it's also like somehow, before I take global sections, it sets for equivalent. So I have some a compacted Lie group. I basically told you that.
And what's the role of the base?
The base is just what I take global sections of.
Okay, so it's also continuing.
Right. I mean, so what Gepler and Meyer do is you can. Let me leave it. E over and Q such that whenever you have an oriented elliptic curve, you can ask for its classical elliptic curve, just essentially by passing by 0, such that 0 B is isomorphic to the Tate elliptic curve. So this gives us a map. Laughing once again to global sections. We get this map TMF to KL. So this really enhances this topological Q expansion map, which in turn enhances the ordinary Q expansion. But of course, now there's an immediate corollary to this, using this theorem I told you about before, which is there's, in fact, global version of this expansion.
Is there a uniqueness theorem implicit in that? That there's only one way of enhancing it?
Yes, so this oriented elliptic curve we get is unique, but it's unique with, I think, quite a few properties. So it's more than just, I think, the statement that it's restricting to pi 0. But it is, yeah, I mean, with a couple more properties.
And what about the map?
Sorry,
Is the map?
this map here.
Yeah, the equivariant. That somehow, I mean, that should also be.
Yeah, right. I'm not so sure. So you can state some uniqueness property of this map, also in terms of obstruction theory. That's another way to approach this map. Here, I don't actually know. I don't know. I mean, like this before this theorem, this is not even defined. I mean, you might have other definitions for this, but this is, I would say, just while it was true that here we just took KO and we base changed it, it's not true for this theorem. This KO is not base changed from, let's say, genuine equivariant. Real behavior. So I wouldn't even, I mean,
So what is G equivariant?
Hmm?
What is G equivariant also?
I mean, they're described by the global sections of this Tate curve.
Do you know what they are?
No. I mean, I don't think I've thought about it that much. Probably you could say.
You said they're not exchanged, so we.
Yeah, no, I mean, I could tell you, for a finite group, I could tell you. For a finite group, I could tell you exactly what they are. And maybe I could tell you afterwards. At S1, I don't actually know.
Else, the global sections of
Yeah.
the curve, I think they're just base change.
Okay. Base change from what?
I mean, the curve S1 fixed point of TMF, tensor over TMF, KOQ.
I mean, that's true, yes.
S1 fixed point of KOQ.
You're saying it, I mean, I guess you're saying this. Yeah, I think that's right. Yeah, of course, that's right. Yeah, that computation is actually just already in this paper. Sorry. Yeah, and then finite groups I must. It will, I guess, basically appear later. Hopefully, let's see. Yes. So as another application, let me just say this quickly. Another application. We can now compactify. Exactly as in the previous case, we can just base change this map along the map to KU power series EQ. And in this way, we give another construction. I think as far as I'm aware, this is the first construction that's purely in the world of spectral algebra and geometry, and that doesn't use tools from abstraction here.
One question. So this map of TMF to KOQ has
Yeah.
been there before.
This one, yes.
So, but I mean, compactified MLO in this style, we just because
I mean, we should compactify and then take global sections, right? Not take global sections, but push out. Like you're not gonna.
is the map from spec KOQ to MLO the same thing as a map from TMF to KOQ?
That is true. But as far as I'm aware, we wrote this down in this paper as well. I don't know if that was in the literature report. But yeah, that is true. I mean, it's yeah. That is true.
Respect to elliptic curves, they are strict, so that you have
Yeah.
strict inverses, so that the action is the
Yeah.
inverses already.
Yeah. As Abelian group objects, they're really strict Abelian objects. Let me give one more theorem, which I think might be interesting. Can we also think about sort of real C2 applications of this construction? Namely, we prove there exists a C2. Let me say here naive. So I really just mean a spectrum of C2 action. Unit 1, 3, and 2 expansion maps. Unit 1, 3, KU. KU. Okay, so here I have joined the primitive third group of unity, and here I have somehow. And these correspond to evaluating at the ramified and unramified. Clasps. And I want 3, 4. So this is a moduli stack oriented elliptic curves with level structure. This has 2 cusps, so 2 points at which we have to compactify. And these 2 maps are the maps we get when we compactify and then evaluate at that point.
Is the E,
Sorry?
did M1 3 work, or M1 E work?
Yes. Okay. And let me just say, C2 structures like this spectrum have been constructed in the literature before, for example, by Mike and Leonard. And I think we don't know if this C2 structure we construct on the spectrum is the same, but we think it should be.
So maybe I missed this as well, but now we're talking about this C2 thing. Your map from spec KU, whatever, like C2 orbit to MO, does this come from C2 quotient on both sides where there's a...
You should think about this as just saying like every elliptic curve has a C2 action, just given by applying -1. And if you think about giving an elliptic curve where the C2 action is, it's precisely a map just out of the stack quotient of the source into the moduli stack of elliptic curves.
So MO is not naturally like a C2 quotient of some
No.
2 covers.
All right, so now I want to tell you a little bit about how we construct this oriented elliptic curve, because I think it's a nice story about the way that as I've expressed it here, right, the world of spectral algebraic geometry and this theory of oriented elliptic curves gives us consequences for equivariant homotopy theory, but in fact, our construction also goes the other way around. It uses somehow insights which are natural or which you can see from the perspective of equivariant homotopy theory that are maybe not so clear if you're just thinking about oriented elliptic curves. So in fact, our construction somehow operates on the level of p-divisible groups and not at the level of elliptic curves. So let me quickly explain what I mean by that. So once again, these p-divisible groups are spectral enhancements of p-divisible groups from arithmetic geometry. Reoriented. G from some categories, so infinity category, globe, thin out, which is in 1 second, to commutative algebras over R. So let's say this is some p-divisible group over some ring R. My notation for this is it sends some finite group A, G. So what is this? This is just the subcategory of this spanned by Eilenberg-MacLane spaces on finite groups. Like BA, this is just not even Eilenberg-MacLane spaces. This is really just BAs where A is a finite union. So first of all, G preserved products. And 2, G sends short exact sequences. Short exact sequences. To push-outs. And also the vertical numbers. So those associated to injections of finite union groups are finite flat. So in particular, G of A for all A, because this math is finite flat. You're really right. Right, so each of these is a flat algebra. This. Already here we somehow see the connection in a very concrete way because these are like, for me, this is basically some sort of global cohomology theory. I guess it should be a global cohomology theory with some properties.
So are these finite groups or finite group schemes?
This is just finite groups. And then, once again, you say G is oriented. If any p-divisible group, I can associate somehow its formal parts. Again, intuitively, you should think about it as completing around the origin. And once again, I want this to be R. It's complex oriented. and completion of R is the same as the full informal group. That's formal groups. But in this case, we can make this more explicit and somehow more familiar to Equivariant homotopy theorists. Equivalently, Larry shows that E is oriented if R is complex oriented, and this equivariant homology theory satisfies T is and the map from B A to G H A is completion, derived completion, and no obligation.
Does that HA also mean homotopy fixed points?
Yeah, so in this, because I have for BAs, I have canonical. All right, and so these sorts of things are, I guess, familiar. That's the sort of things we study in equivariant homotopy. So, for example, look at the multiplicative group scheme over some complex-oriented R. And out of this, I can take all of its torsion points. Taking torsion points. I get a p-divisible group, and in fact, that's the typical way you get p-divisible groups. You take some Euclidean variety, extract all of its torsion points. And this is a over AU algebra. This thing, and in fact, over this KU, take this over KU, and I evaluate it now on some finite abelian group, precisely get usual complex equivariant KUs. All right, and so just as I can take the torsion points of GM, I can also take the torsion points of an elliptic curve. And the reason why we discuss these p-divisible groups is because the classical Tate theorem tells you that the deformation theory of an elliptic curve is essentially the same as the deformation theory of its associated p-divisible group. And Larry proves a spectral version of this. And working up the Postnikov tower, this tells us that really, because we already have Tate curve, we just need to extend its p-divisible group. Yes. Okay. All right, it's a consequence of the spectral theory.
So for example, did you mean KU of BA? Okay. I mean, you have some equivalents in mind, which.
Yeah, I just mean here really equivariant K theory of the group A, not the KU of BA. So the following squares. Zero, 2. You can take its associated p-divisible group. This lands in something called BT2 because p-divisible groups are sometimes called with sign Tate. And you can look at oriented p-divisible groups over R. So this is not really an object in spectrology or geometry. There you have elliptic curves, oriented elliptic curves. This,
The B and the T do not have anything to do with the B's and the T's, which have occurred earlier.
it's not Tate. That's right.
There's also a T for a group.
Or is it a binomial claim? But it's not.
And so to be completely precise, I should say that here R is P. So really, we apply this theorem to the P completion at every P, and then we use arithmetic fracture square to conclude we actually have an elliptic curve over KU trying Q. Okay.
So
anyway.
anyway, that's necessary with people.
Um, I think so. But of course, I was wondering about this because, I mean, what we use to make this arithmetic fracture square argument work again is like this co-representability of elliptic curves by TMF. And so you should be able to, like, instead of doing it in the special case we did, you should just be able to do it in general. And then you should get some here, like you should get some result, right? Which is precisely what you need.
When did it get from?
Right, so what I was saying is, we really want to construct a big curve over this thing. And well, what we actually do is we completed all primes. We apply this argument to reduce the constructing a P divisible group, and then we glue them all together with the arithmetic fractures.
When you define P divisible group, it was a difference of P.
Yeah, I mean, I think this is actually true. Here I actually mean little p. But there's somehow no difference. So if you're P complete, the P divisible group, then this is also a little p divisible group. They're equivalent. Yeah, but like the more usual way of thinking about it would be with little p. Okay. So now having made this simplification, I can now connect to equivariant homotopy theory. So we have to lift this P divisible group associated in K theory to KU join Q. So this object was studied by Katz and Masur. So, and the very important thing is that they actually proved that you can actually define the P divisible group associated with the Tate curve already over Z adjoint a polynomial variable Q. This thing. In fact, it's not just defined over this thing lives over Z. Instead, you can in fact already define this. Sorry, yeah. Okay. All this is E are specific. So this is some P divisible group defined now over Z adjoining Q plus minus 1. And in fact, we just have to lift this to KU adjoining Q plus minus 1. And what they also showed, Katz and Masur, is that it's in the following Schrödinger sequence. This is the formal part of this p-divisible group. And here you have some italic. Okay. So essentially this is an italic extension of the multiplicative p-divisible group. And the multiplicative p-divisible group we know how to lift to spectral algebraic geometry. It just is, as I told you before, nothing other than equivariant K theory. So now we have the following slogan. Now, extension of p-divisible groups. Right, so this is a concept very much in spectral algebraic geometry, but it has an analog in equivariant. It should correspond to evaluating on orbital loop spaces. So I don't know to what extent you can make this slogan into an actual theorem, but there's one instance of this, which is Lurie in elliptic 3 shows that if you have a trivial italic extension, then this slogan is literally true. And he uses that to explain the loop spaces in the target of the HKR vector. And so let me give you a second instantiation of this observation. Let me define glow app to be just like glow fin app, but now instead of finite abelian groups, I take compact abelian groups. But again, it's just a subcategory of spaces on B, A, where A is a compact abelian group. Subcategory of spaces. And let me define this to be free sheaf cells. So this is some analog of global spaces, globally equivariant spaces, but for the family of abelian compact groups. In fact, that's exactly this.
It's still finite, right? The abelian groups.
No,
No,
no. Here I really need all compact abelian groups.
but you still write that many covariants.
Exactly. Yeah, it's the result of Charles Resk that this is possible. He computes like maps between classifying spaces, between compact abelian regions. Really, like I think he calls them. It works for like torus times a finite. The maps between the classifying spaces are exactly the maps. Okay. So I have an evaluation function going to spaces, and it's a range. I'm going to call R. And of course, just our normal facts about this sort of game tells us that RBA is nothing other than D, viewed as a representable in applicable spaces. And I make the following definition. It's a signification construction. That's a notation inspired by work of Tate and Freiberg. And okay, and what do? So I take my BA for A some finite abelian group. I just view it as a space. I take the loop space on it. This loop space admits an action circle just by rotating loops. I mod out.
This is the free loop space.
Yes, the free loop space. And then I include this back into output spaces. It's a slightly esoteric construction, but let me make some observations about it. I take the simplification point, I just get BT. So loop space of the point is a point, then you modify T, you get BT, and then you take R. So this is really BT as an object at global space. More generally, if you take sig some BA, then you get the disjoint union over all A and A of BT times A over A mod the subgroup generated. And that's the crucial observation. This is an observation implicit in Barrington's work, and then made explicit by Brett, and then taken out and developed a lot by Chen 1. He tells us if we take equivariant KU, which is a cohomology theory on all global spaces, so in particular at global spaces, and I apply it to the simplification, 0, then this is precisely the Katz-Preserve hedonism. So once again, we see that somehow this tal extension we were seeing in the definition of the Katz-Preserve hedonism is precisely coming about by applying the cohomology theory associated to this p-divisible group to some sort of uniform group space. Okay. And of course, now it's no mystery how we enhance this to a p-divisible group in the spectral sense. We can just remove the pi 0. You have to do an exact proof. After all these reductions are said and done, we prove that this is an oriented p-divisible group. Lifting. Okay. Right.
That's why you say it's sort of a canonical object, right? It's
Right. Yeah.
Making it.
Somehow already equivariant K theory knows about the. Yeah. Okay. I think we'll stop there. Questions?
So historically, I mean, so people have looked at so the circular equivariant Tate cohomology of the free loop space. It's kind of an ingredient here. That's not strictly speaking a cohomology theory.
Yeah. So
What you're doing is modifying that idea to
I mean, if I actually wanted to define a cohomology theory now, I would just write formally turn into a cohomology. But I guess right. So the point to be made is, in some sense, what we're doing, right, is we're at least saying that. I mean, one point of this global game you might say is like, let's say in this generality, we're really just working with a subcategory of spaces. So of course I can define right my cohomology theory by just saying what it does on a point, and saying by descent I know what it does everywhere else, and then I get Borel theories. And here we're somehow picking some object, some class of objects where we don't want descent, and then we extend from by descent from there. That's somehow one way to think about like equivariant, why equivariant homotopy theory has anything to do with this. So,
Let's say again, where is the input somehow? What you have to start somewhere, right?
what do you mean?
It's, I mean, you can extend. You can say, okay, you don't want descent from everything, so you have a
Yeah, so it's
Some
precisely an assignment essentially for every BA.
Right.
For
And
A,
then-
finite abelian.
Right.
I mean,
And why do you know what to do there? Say that again? That's because you
I
have.
mean, it's essentially, I mean, you don't. Functors like out of this with certain nice properties are these p divisible groups.
Hmm.
So these you have to construct some way. We started with the fact that we knew what equivariant K theory was, or another way, just we knew we could define a p divisible group associated to the multiplicative group scheme. This is just an object you can define in spectral algebraic geometry. And then we applied this construction.
Before loop space, that's the free loops and the certain one, right?
Yeah, it's, I guess,
Can you say something more about that using the word orbital pairing?
right, so, I guess I call it this also because, I mean, from a stacking perspective, if I have some stack, which you might think of as representing some global space or having some underlying global space, then its simplification should be you take the stack of palms from BZ to X, and then you mod out by this circle. So this is what's often called like the inertial orbifold.
So where's this is happening?
So this is happening, let's say, in topological stacks. If you're at finite abelian groups, essentially like so this is a formula which should work also for basically any global homotopy type for any topological stack. So in particular, I think that should be the right guess to extend this away from finite abelian groups. But for finite abelian groups, we essentially do a trick. We say, actually, it's a full subcategory of spaces, and essentially, like, if you want to do some stacking construction, well, you could just do like, this space level construction is already stacked. If you take BA and you take its inertia stack, you precisely get this. And if you did this same construction, so I guess the loop space, that's actually what you get. That's before you take the T action. And if you did the same thing in the world of stacks, you would get the same answer. Just under identifying this point with its associated stack.
Here you've sort of done the simplification to construct an italic extension of mu infinity.
Yeah.
Can you like, are there other interesting p divisible groups for which you simplify like this?
Yeah, so that's something which, so what we actually prove is that if you take any p divisible group, we simplify it, it's again a pre-oriented p divisible group. Of course, the question is it oriented? What we actually use to prove that it's oriented is that we already know the short exact sequence. So we already know this result, and you can really check if something's oriented essentially on pi 0. And so this already tells us that the formal part is precisely that coming from KU. The formal part is all here, and we just have this italic up here. I was actually just reading something where I never really seen this, this simplification construction considered explicitly in some, people thinking about chromatic homotopy theory and its p divisible groups. But then I actually saw it in some notes by Eric Peterson of some seminar that happened, I think, at MIT. And I don't know, let me just say, we hack our way to the proof that this is oriented. Maybe if you understand this construction better, you can just prove it's oriented. It kind of seems like you should. This simplification should somehow always be implementing this sort of italic extension. That would be the idea. I don't know if that's actually true. And then you would know that the formal part is somehow base changed from the formal part. That's all you need to know it's oriented. Yeah. But
Because orientedness is like a formal, the formal equivalent.
exactly. Yeah, and somehow the fact that we've only added something at tau means the formal part here of this thing is the same as the formal part here. And that's the formal part of Gn, which is precisely equivalent to root line. Yeah,
So now you have an E-infinity ring map from this uppercase T little mf.
Yeah.
To your K with parentheses Q together. Speak up.
yes, I mean, I think I've noticed.
But in particular, so if you now pass to the connected TMF, so little TMF.
Yeah.
Will also map to this, and will of course also map to the one where we have little k.
Yeah,
But in fact, that map factors through a higher connected cover where you take, where the target is the sum over non-negative I of the 8th suspension of little k. I'm at the prime 2 now.
okay.
I know how to construct that map as a multiplicative map in the homotopy category, but I don't know how to make it an E-infinity map.
Okay.
Can you somehow see some information about connected covers here? We're leaving the steps. So, for example, the discriminant would map to the bot element in degree 8 on the 16th suspension.
I'm not sure. I mean, like this map, right? The E-infinity version of this map already exists before all this.
Yeah, but I'm asking for a passage not to the connected cover, but to some further. I mean, the target I'm describing is not just the connected cover of that target. This would be a map which would be interesting in cohomology. It would be easily right what this map would do in homology or cohomology. But I don't know that this particular map is a spectrum, is an E-infinity ring map.
I see. I guess.
Okay, I think that,
Yeah.
let me ask a bit.
Sure.
Any more questions? Well, thank you very much.